Imagine this. What if the invisible stuff shaping the universe, the stuff we call dark matter, was once pure energy? Sounds wild, right? But a bold new theory from Dartmouth College is flipping the script on everything we thought we knew about the mysterious force that makes up most of the matter in our universe. This story begins not with dark matter, but with energy. And from that energy, dark matter was born. Before we get into the theory, let's talk about what dark matter even is. You've probably heard that dark matter is some kind of invisible stuff lurking in the cosmos. It doesn't glow, it doesn't reflect light, and we can't see it. Not with telescopes, not with X-rays, not even with gamma rays. It's like the ninja of the universe, stealthy, silent, but powerful. And yet, dark matter is everywhere. It holds galaxies together like cosmic glue. It sculpts the universe. It outweighs all the normal matter, the stars, the planets, you and me, by about 5 to 1. That's right. If the universe were a pie, normal matter would be a teeny tiny slice. The rest? Mostly dark matter. So, where the heck did all this dark stuff come from? That's been one of the biggest puzzles in physics for decades. And here's where the plot twist comes in. Let's rewind the clock back. 13.8 billion years ago, the Big Bang. We're talking temperatures so hot that nothing had mass yet. Particles were zipping around at the speed of light. Space itself was a boiling soup of energy, chaos, and possibility. In this wild party of a universe, most particles had no mass. They moved fast. Think, tiny beams of pure energy, flying everywhere like cosmic espresso shots. These particles were similar to photons, the particles that make up light. But they weren't exactly photons. They were something else. High-energy, massless particles that we haven't seen since. And here's the new idea. What if some of those fast, massless, light-like particles, let's call them zippies for now, started bumping into each other? Not just random collisions, but special ones, magnetic, almost. Imagine two spinning tops colliding in just the right way that they lock together. Like two puzzle pieces snapping into place. That's what Robert Caldwell and Guanming Liang think happened. These zippies didn't just smash and bounce. They paired up, and when they did, everything changed. Let's pause here and talk about what Caldwell and Liang actually did. Caldwell is a physics and astronomy professor, and Liang is a double major undergrad in physics and math. Together, they cooked up a model that rewrites the origin story of dark matter. Their idea? In the early universe, these zippies paired up in huge numbers. When they did, something weird happened, something that, if true, explains both the mass of dark matter and the drop in the universe's energy over time. The big surprise? These particle pairs didn't just slow down. Their energy plummeted, like crash-landed, from sky-high to basement level. The analogy they use? Imagine a double espresso cooling into cold oatmeal. 1 second, you're a jittery, high-speed beam of light. The next, you're a cold, heavy lump. Exactly what we think dark matter is. And boom, dark matter, born from light. This is where the magic of physics kicks in. You might be thinking, okay, but how can two light-like particles just lose energy and gain mass? Isn't that kind of weird? Yes, it is. But nature already has a trick like this. It's called a Cooper pair. In some superconductors, two electrons can pair up when it's cold enough. Alone, electrons hate each other. But under the right conditions, they do a little quantum dance and become best friends. These Cooper pairs move in a weird, frictionless way, kind of like ghosts gliding through walls. And crucially, when they pair, their energy drops a lot. Caldwell and Liang took inspiration from this and asked, what if something similar happened in the early universe? Their math says it could. This is the heart of the theory. The paired-up zippies didn't just chill out, they transitioned. It's a phase shift, like steam becoming water or water becoming ice. One moment, you're pure kinetic chaos. The next, you're a heavy, sluggish particle that doesn't interact with light anymore. And this crash in energy? It did two huge things. First, it created mass. These paired particles went from zero mass to something very heavy. exactly the kind of mass dark matter needs to form galaxies. And also, dropped the energy density. The universe was way denser right after the Big Bang than it is now. This theory explains why some of that energy turned into mass, and the rest dropped out like a bottoming stock market. That's why the universe is so cold and clumpy today, instead of hot and uniform. Now here's where it gets juicy. This isn't just a wild guess. Caldwell and Liang's theory actually makes a testable prediction, and that's rare in the world of dark matter. Remember the cosmic microwave background? That faint glow from the Big Bang that's still zipping through the universe? It's like a baby photo of everything. If these particle pairs really formed, they would have left behind tiny fingerprints on the CMB. Not visible ones, but changes in pressure and density, little clues in the data. And guess what? We already have satellites and observatories looking at this. Projects like the Simons Observatory in Chile and upcoming ones like CMB Stage 4 are studying the CMB in ultra-high detail. If Caldwell and Liang are right, the evidence might already be sitting in the data. We just haven't looked at it the right way yet. One of the coolest parts of this story, it all started with a question. Liang, the undergrad co-author, was in a solid-state physics class at Dartmouth when he read a 2023 paper about Cooper pairs and the early universe. He reached out to the authors and asked a simple but brilliant question. Hey, did you guys test this idea at non-zero temperatures? Turns out they hadn't. At the same time, Liang had just learned a mathematical trick in class that could help extend the model. So he brought it to Professor Caldwell. They ran the numbers. And boom, out came this beautiful theory that ties together high-energy physics, superconductivity, cosmology, and the mystery of dark matter. Let's step back and think about what this theory would mean if it's right. Dark matter didn't come from some weird particle we've never seen. It came from familiar physics, particles pairing up, energy dropping, just like electrons in a superconductor. It was born not from destruction, but from a kind of quiet union. Light became heavy, speed turned into stillness, hot became cold. In other words, the stuff that shapes galaxies, stars, and you may have started out as pure light. That's not just science, that's poetry. So let's zoom in. What were these zippies, these ultra-fast, massless particles that allegedly turned into dark matter? Caldwell and Liang don't name them outright, but they describe their behavior in mathematical terms that let us imagine what kind of particle this could be. It's not a photon, not a neutrino, and definitely not one of the standard particles in the physics textbooks. Let's call it a prion for now, not because that's technically accurate, but because it gives our mystery particle a name. These prions were everywhere in the early universe, and because they had no mass, they could travel at the speed of light. But they weren't just chaotic rays shooting randomly. They had a trick. They could spin, and spin is crucial. Here's why particles with spin can attract or repel each other based on that spin, kind of like magnets. When two of these prions had opposite spins, it set up a perfect situation for attraction. They were drawn together, locked in a dance that pulled them into a bond. This spin-based pairing is at the heart of the theory. And when you model it mathematically, something strange happens. The paired system becomes more stable than the two free particles were before. Translation: energy drops, mass emerges, dark matter is born. Now, let's talk about what this theory isn't. For decades, the two biggest candidates for dark matter have been weakly interacting massive particles and axions, which are tiny, hypothetical particles that solve problems in quantum mechanics. Whole experiments have been built to try to find these things. But here's the problem: we haven't found them. Weakly interacting massive particles detectors have been running for years without a single hit. Axion searches? Same. Caldwell and Liang's theory doesn't need weakly interacting massive particles or axions. Instead, it says dark matter came from particles we don't need to invent from scratch, but from basic principles of quantum mechanics, just used in a clever new way. This is like realizing that instead of needing some alien ingredient to bake a cake, you just needed to mix the eggs differently. It's simpler, and physics loves simplicity. Okay, let's get back to that glowing baby picture of the universe, the cosmic microwave background, or CMB. This thing is everywhere. It's the faint afterglow of the Big Bang, and it's filled with information about how the early universe evolved. Tiny changes in temperature and density in the CMB reveal how matter clumped together, how galaxies formed, and even how gravity behaved in the first billion years. So, if this light-to-dark matter transformation really happened, it would have left clues in the CMB's subtle fingerprints. Here's the cool part. Caldwell and Liang's model predicts that their hypothetical particles, when they became dark matter, would have been cold, slow, and pressureless. That last part, pressureless, is a big deal. Most things in the universe, like light or radiation, have pressure. But these dark matter particles? They don't push or pull. They just are. And that makes them leave a special kind of signature in the CMB. The one we can look for. It's kind of like finding fossilized footprints in ancient rock, only we're doing it with photons. And thanks to new telescopes like the Simons Observatory and upcoming projects like CMB Stage 4, we might be able to spot these dark fingerprints soon. Let's go back to that superconductivity idea for a moment. When electrons form Cooper pairs in a superconductor, they do something crazy. They stop resisting. They move without losing energy. That's why superconductors can do all kinds of magical sounding things, like levitate magnets or carry infinite current loops. Now imagine something like that, but on a cosmic scale. In Caldwell and Liang's model, the early universe was like a giant conductor, filled with these high-energy particles flying around. As they cooled, they started to behave like electrons in a superconductor, pairing up, dropping energy, becoming stable. It's like the universe went through a phase change and became superconductive to dark matter. And if that doesn't give you chills, nothing will. You know what's amazing? The universe is full of phase transitions. Water becomes ice. Steam becomes rain. Atomic particles bind into atoms. Chaos turns into structure. This theory just adds another one to the list. Energy becomes dark matter. It's not even the weirdest transition we've seen. Physicists already know that particles can change their identity depending on temperature and environment. Neutrinos oscillate between types. Quarks bind into protons. Photons can turn into electron-positron pairs. So why not this? Why not a pair of massless particles suddenly deciding to become the invisible mass holding galaxies together? It's weird, but it's also very universe. Let's step outside the lab for a second. There's something almost poetic about this idea. Energy turning into dark matter. Energy cooling into structure. Chaos becoming the quiet skeleton of the cosmos. In the real universe, energy may have given birth to the very dark matter that lets galaxies exist. Without that quiet transformation, we might never have stars, planets, life, or minds capable of wondering about it all. That's a beautiful idea. So where do we go from here? Well, the theory has already passed the first test. It works on paper. The math checks out. It doesn't require breaking any known laws of physics. And it even connects neatly with existing ideas in quantum mechanics and condensed matter. Next step, observational evidence. That means mining CMB data for those unique dark matter signatures, simulating galaxy formation with this kind of dark matter, and looking at gravitational lensing patterns, how dark matter bends light, to see if it matches the predictions. If any of these line up, we could be on the edge of one of the biggest breakthroughs in cosmology in decades. And that would be wild. We know cosmology can get dense. There's a lot of math, a lot of weird particles, a lot of talk about phase transitions and temperature gradients. But at its core, this story is simple. It's the story of a universe that started hot, wild, and fast, and slowly calmed into something stable, beautiful, and mysterious. It's the story of how the invisible scaffolding of the cosmos might have come from the simplest ingredients imaginable: light, motion, spin. And it's a reminder that even the deepest mysteries, like what 85% of the universe is made of, might have surprisingly simple beginnings. So what if dark matter really is the end result of light slowing down? What if all the stars, galaxies, and cosmic structures we see are the side effects of a single, elegant transformation? When energy dropped, and the universe grew quiet enough to let matter form. What if the universe is more like a symphony than a machine? Music born from vibration, from patterns, from the graceful cooling of the hot into the heavy. That's the story this theory tells. And it's just the beginning.